Hi everyone, welcome to a new Rhino user webinar. I'm Pedro, and in today's session, I'm excited to introduce Elena Papadopoulou. She will explore the new Rhino 8 scripted environment, focusing on the Python 3 features that enable direct integration of machine learning models, such as regression and classification. With Rhino 8, these models can now run directly within the platform, eliminating the need for external plugins and improving workflow stability. A bit about Iliana. She's an architect and software developer, currently working at Reop. She has led initiatives in spatial computing, machine learning, and interface design. Today, she'll showcase one of her projects, LearnCarbon, which integrates data cleaning and model training using tools like NumPy, Pandas, TensorFlow, and Keras. That's all from me for now. So just a quick reminder, there will be a Q&A session after Iliana's presentation. So get your question ready. Iliana, the floor is yours. Please feel free to start when you are ready.
Thank you, Pedro. I won't say much about myself because you did a really nice introduction. I'm just going to say I'm happy to be here and present this methodology and project. A bit of the outline of the presentation. We'll go through a bit the background and the motivation of the project. Then what we mean with machine learning in this case and what exactly it predicts with which inputs. After that, I will explain the data preparation and the dataset we selected and how we cleaned the data to train the model, along with the training of the model. And the last two will be shown in Python on Google Colab. So we'll be able to see the code. After that, how we initially integrated with Rhino and what updates we could do with Rhino 8 now. Finally, I will mention alternative use cases because the goal of this presentation is to contextualize this technology. And as a disclaimer, I'm not a machine learning engineer. I just adopted this methodology and tried to implement it in practice. So the project started as a hackathon, AC hackathon in Copenhagen. And it started when I was talking with Kritika. And of course, you can find from the QR code our paper that we have documented the whole process and the names of everyone, the affiliations and everything. So the process started with Kritika and myself discussing what we can do in the hackathon, and she was very much into carbon assessment and the tools created around that and climate tech. And I was using quite a lot of machine learning for different tasks in the AC industry at the time, so we decided to combine these two. And I think we found the best team to do that, which is and a very positive one, as you can see in the photos. And the motivation behind it is mostly, just a second to find my notes. Yeah. So we focused on embodied carbon and specifically on the structural material, which is the highest contributor with a percentage of 50 to 80%. And as you can see on the graph on the right, the opportunity to change the environmental impact decreases while the cost of changes increases as we move forward on the project. So currently most LCA and carbon assessment tools do not address early stages, which is the phase where it's actually really critical. And usually this analysis is undertaken when most decisions have been made and is therefore difficult to propose any substantial changes. We did a bit of literature review to understand what tools are out there. Right now I'm showing just 4, but there are way more. But most of them either need a lot of details to create an assessment, which is not very appropriate for the uncertainty that there is in early stage of an architectural project. Or they are based on a lot of assumptions and abstract geometry, which doesn't give a very accurate result. So we wanted to find a solution to address this, and to that to instead predict instead of estimate. And yeah, machine learning can be a quite broad term. There's also a lot of hype around generative AI, but what do we mean in this case? In this case, we mean supervised learning, and specifically two models, classification and regression. And basically a neural network with multiple inputs and outputs. And specifically, these two models, the first one, which I will focus on show more as a case study, gets an input of a conceptual massing model and predicts the global warming potential. And the classification model from a conceptual model, so that's an interesting thing about machine learning, that we can, once a model is able to learn the first relationship, we can then inverse the relationship and say from a conceptual massing model from Rhino and a target GWP value, what kind of structural material should we use to achieve this? And specifically, the inputs are this. So we have the building type, we mean typology with that, the location in the world, the GFA, a number of floors, and the material of the structure for the first case. And it's more relevant now because we previously used hops running on a Flask server to run the Python scripts with all the necessary dependencies, while now we can run them directly from the Rhino script editor, which makes the process way easier. And the first step of the process was to select the dataset. That was the embodied carbon benchmark study, which is it's this one that we used. And there were some problems with this dataset specifically, and with the problem we were trying to solve. So this is more of a proof of concept, and I will explain what the problems were specifically. So first, we needed to add material of the structure which wasn't included in the dataset, and there was a specific logic to do that. The process was led by Karim and Kritika, who are experts on the subject, so I'm not going to expand too much on that. We also needed to drop some entries, some buildings that were classified as generic or industrial, and they didn't have a lot of examples in the dataset, so the model could not actually learn these typologies. So we need to drop them. So we kept residential and commercial as typologies. And the data from this dataset are not enough for a global carbon prediction tool. So there were some biases for, there weren't enough entries for large buildings or very tall buildings, and there weren't many entries for specific locations of the world, and also the location was based on continent, which is not enough of detail. So in the future, we would like to train it with more detailed data and more data. So yeah, I'll pass to the to the code to show you. So first, we import all the necessary libraries, either for visualization, for data management, Pandas and NumPy, and TensorFlow, of course, for the models, joblib for saving the model, and the scalars. And the initial data setup was not very fancy, very basic. We just kept the columns that made sense in our case, and dropped, as I mentioned, the values that didn't. So we ended up having something from something like this, that the initial data set with categorical data here, to something like this, which are the final data used for the model. yeah, and also we converted the information into from string data into numerical. We use Pandas for that, so we can pass it to the model that doesn't understand strings. And finally, what I mentioned with the categorical data based on a certain logic of instead of having a categories of areas, for example, with bounds, we had an exact number. And that's, of course, an estimation based on the logic we had from our domain knowledge from architectural practice. Then finally, sorry for the, yeah. Finally, saving the data, this is the one I showed, and starting with the plots to understand what kind of data we have. So splitting it into numerical and categorical, which is numerical is, data with numbers, and then categorical is with classes, categories. And this first plot, the pair plot from Seaborn library, helps us understand and visually inspect the relationships between the features, which is critical to understand which features we should use. The diagonal, these three parts are a box plot which shows distribution of the data because it's the same parameters. So, for example, we can see that the lower buildings have way more representation than taller buildings. So probably the predictions for taller buildings will not be that accurate, for example. For the rest of the grid, a linear upward trend would suggest a positive correlation between two features, while a downward trend would suggest a negative correlation, while a random scatter will show no correlation. And in our case, we would like correlation between the output CO2 and the input parameters. So that can give us a hint if the model will be able to learn this relationship, if there is a correlation there, while we don't want high correlation between input features like number of floors and area, usually. And moving to the next plot, again, to understand the data, the correlation matrix. The positive correlations, in general, again, we want correlations between input data and input data and output value. This is a symmetrical plot that helps us understand. Yeah, sorry, I got distracted. The values closer to -1, so very dark, so negative correlation, while values closer to 1, so positive correlation. And then we can start understanding, for example, prove our assumptions that what we call here building construction type, which is the material of the structure, is highly correlated with the CO2. And also any other interesting aspects of the number of floors is highly correlated with the location. And also the material of the structure is correlated with the number of floors because you can, we have some limitations with certain kinds of material. Moving to the actual model, we use scikit-learn for to use the scalars and the algorithm to split the dataset to train and test. First, we identify our input data, which is all of the data in the dataset, all of the columns except the CO2. And we use a standard scaler to transform the data from all the different columns from whatever range there are to have a mean of 0 with a standard deviation of 1, ensuring that all features are on the same scale, helping the model learn, basically. And then about the output, which is the CO2, we use the min-max scaler, which is from 0 to 1. And that I will mention this a few times. That was a bit of a back and forth process of understanding what is best in this specific case. So then as I mentioned, we split the data into train and test with a 20% test size of the data set. I think the total number of entries were 700 something. Yeah. And then the actual creation of the model, a sequential model from Keras, TensorFlow. This was, we used 3 dense layers, and this was a process of adding layers until the model were starting overfitting, so memorizing instead of learning. Usually the Adam optimizer for compiling the model and the mean squared error loss function would work, but there are a few more that you can explore if you're trying the same. So yeah, this is the summary of the model with the 3 layers. And yeah, the output of the last layer represent each one because we have one output. Then we trained the model for 200 epochs, so 200 iterations. And I have some plots here to understand, excuse me, to understand if the model was able to learn. So from this plot of the error, the mean squared error, we can see if so the training loss is decreasing, which means that the model is learning, but also the validation loss is decreasing, which means that the model does not overfit or underfit, but it's actually learning. So it is able to generalize from unseen data from the test set. If, on the other hand, if the validation, if the training loss was decreasing and the validation loss was increasing, that would mean overfit. So the model was predicting well on data that it has seen before, while it couldn't predict data that were new. While if both curves were high, that would mean that it was underfitting, so we basically needed more data for the training. This plot is basically, plotting the one axis, the ground truth values, the actual values of the CO2 and the predictions. So a perfect model would be a perfect diagonal line with 45 degrees. And the deviation within this diagonal show the error. So we can see that we are doing quite good, but there are still some values that are deviate quite a lot from the actual prediction. So probably this is because of the bias in the dataset. So we can visually assess how well the predictions match with the true values. Giving an indication if the model was able to generalize the test set. And finally, this plot, the prediction error is calculated from the difference between the predicted values and the true values. And in general, of course, we want everything to be closer to 0, which is most of our cases here, but there are still some values that have quite a big prediction error, as I showed also from the previous plot. Moving into, I forgot to show this. We save the model and the scalars as a critical step because we are going to reuse the scalars. And then moving to the setup, the tech stack we had before. Through the hackathon as well. That is not playing, but that's fine. I will show it a bit more. The user flow is after designing a 3D massing sketch in Rhino, the user can proceed by selecting and defining the inputs. and the type of prediction. So the first model or the second model. In this case, I showed the first model. So yeah, I will showcase this. And once the data is passed, the Flask server automatically detects the changes made to the inputs and reruns the code, which loads the machine learning model and the newly indicated inputs. So this is showing the code as well. So the hops is a wrapper that allows running a Flask server and serving data from an external Python instance. So we could run all the libraries inside Python, inside Rhino. But we faced sometimes issues in setting up the system, especially with users that haven't done it before, like new use cases. And a lot of people reported problems. And the UI was built in C# with XAML, allowing for user input. There was a Grasshopper file running on the background to connect to hops. But right now, I will show how the setup is with the Rhino script editor that we can basically bypass hops. So the first step is to install the necessary libraries, which we can either do with the script editor and as I show in this little video, or we can work with PowerShell with the right directory that Rhino defines. This is a great post that helped me a lot, and also define what kind of which version we need. So I had a problem with the compatibility between NumPy and TensorFlow and how I was installing it in Rhino directly. So I use the PowerShell as well. And then in Rhino, we can actually see from here the list of Python packages and judge, understand the versions. And also sometimes I found useful to reset Python 3 in some cases when this is rerun. But in general, this needs to happen once installing the libraries in the beginning, and then the plugin can just run. So yeah, we move to Rhino again. So as I mentioned, we choose a massing model from Rhino, pressing enter, choosing the typical for height, let's say that now it's 4, the location, let's say Europe. These are configured, the typology of the building, let's say commercial in this case, and this is configured automatically from the above inputs. Which model we would like to have. Now I will showcase the first one, the type of structure, and then we press calculate, which is, I'm in debug mode just to show the code. So we call this method, which basically takes all the inputs from the UI and writes a text file. This is probably not the best solution for now, reading and writing text files in a specific directory, but this is the solution I find for now, and it will be nice to hear other ideas. So yeah, it writes a text file with all the inputs and runs a command with run script, which calls the script editor and passes the path. So from Python, which runs the Python script. So from Python, we read this file with the inputs. We understand which model is called from one of the inputs, and then calls the equivalent method. So we load the model. We create a NumPy array with the input data. We scale the data. We load the scalars, and then we scale the data, the input data, so we can pass it to the model. And then we actually run the prediction with the scaled input data. Then, of course, the prediction, we need to inverse transform it to the number we can understand. and write a file with the result prediction again. So back to C#, we read this prediction file and we output it to the UI, which is here. And in this case, right in the command line as well. So it's quite, I would say the integration was quite simple. We upgraded the plugin to Rhino 8 and wrote this code quite fast. So if you have already a setup that uses hops or any other kind of library that allows you to use Python 3 packages, it's quite easy to change it and modify it. And of course, let's find a better solution than writing a text file. So that's it from the Rhino side. And going back to the presentation, I'll give a summary a bit of LearnCarbon. So there is a gap for early stage calculation tools, which is critical for assisting and making more sustainable decisions. And we tackle this uncertainty, either spatial or structural, with machine learning. And it showed that machine model was able to learn the relationship between input features and predictive value. The limitations, of course, as for the data we have currently, is for tall buildings and certain geographies. Of course, we recognize the biases on chronological period and construction framework and operational methods. So for the future, we'd like to retrain it with more recent and well-representative datasets. And also, it would be nice to have presented instead of having one structural material as a class, then have percentages of materials for, let's say, a few different columns. And now I would like to briefly mention another project I worked in my previous job. So that was, again, for a carbon tool, but this time, again, supervised learning and regression. But this time it was to understand the material quantity of the structure. So we were previously using a Grasshopper plugin that was quite slow for the number of buildings that was the standard use cases of the tool, which was around to 15 minutes running for a large urban area. And that really made it difficult to use the plugin, our plugin. So the idea for the model was from building envelopes in urban scale and the selected structural material, what should be the material quantity. And specifically, the inputs included the typology, the kind of structural material, the number of floors, depth, any other kind of geometrical aspects that we can translate into numbers or classes. And then the model was predicting the quantities for slabs, beams, and columns above and below ground and foundation. So we reached around 98% accuracy, which of course doesn't mean anything if we don't contextualize it, but it was enough for the stage we are at. Usually in this project, again, early stage. And it was able to speed up the process from around 15 minutes to 5 seconds. And also, of course, now we are in a Rhino context, but we could reuse this Python code for other softwares as well. And we did that, I'm not going to explain this too much. We did that using a self-organizing map, a kind of old school machine learning. And there is a plugin, Cohonan network in Grasshopper that basically we used it to create the synthetic dataset. So we created a script that could create a lot of buildings with a lot of entries, which we then run overnight with this kind of slow plugin that I mentioned, and then have the final dataset that we could train the model. And I would like to mention that this methodology, I got introduced to this methodology from Gabriella Rossi, who is teaching at IAC, MACAD, and there are some fantastic projects, that you can see more use cases there. This is the seminar from the masters. and there are multiple projects you can check. And also, two students from when I was working there as a faculty assistant made this great project and did a publication in Acadia that you can read more, and it's about robotic pottery fabrication. So maybe a bit more closer to geometrical predictions instead of analysis, kind of. And that was it. Feel free to check the paper for more information or contact me if you think that if you want more information. Thank you very much. And now we're open to questions.
Yeah, thank you very much, Iliana. Let's see if there are questions from the audience. You can paste them in the chat.
Mm.
Okay. Greetings from Ayak. So Edward wants to know if you have compared the results of the tool with calculated results.
The result. Yeah. That is part of the. Yeah, so that is part of the paper and the evaluation phase that I chose not to present here. But we chose, I think, EC3 to compare the results and the deviation from that. So we are quite close in some cases and quite off in other cases. So that shows that the models now are not completely reliable for all cases, but can be used for certain geographies like Europe, that we have way more samples, or USA, rather than other locations that we didn't have many samples. The EC3, I think it was for the US. That was critical leading that process. But you can read the paper for more information.
Okay. Kesava asks, why did you choose jumping between C# and Python instead of JavaScript or TypeScript, considering the Pandas and TensorFlow are available in JavaScript as well?
I mean, I haven't used TensorFlow and Pandas in JavaScript, but I was quite happy. I'm using Python way more. So I don't know how smooth the process would be in JavaScript. Yeah, it's basically I know Python, and I guess that's the reason. But it will be interesting to see an example case if you have that connecting JavaScript with Rhino and how exactly this library is. So if this person has an example, it would be nice to see if they can send it in the chat.
Great. Thanks, Leon, for sharing the link to the GitHub repository of the project LearnCarbon. Andrew
Yeah,
Pat.
thank you.
Yeah, Andrew Pat, would it be possible to harvest data from our BIM models to give a much layer data set?
Yeah, definitely. So that was something we thought about if we had information. So in this project, we focused on abstract geometry. So we don't have a lot of information about the model. We don't have how thick the wall is and what kind of materials and materials exist. So that was the point of machine learning in this case. Of course, when you have more information, you can have models that predict more accurately in a way. So definitely that is a possibility to create a dataset from that, from existing models. Of course, we need to match it with some kind of LCA assessments to create the dataset.
And how did you figure it out? 700 cases for database would be enough at the first place.
Yeah, we didn't at first. So we had to go back and forth and see. So the three plots I showed in the end after the model training showed us that in most cases, the model was able to predict close to the ground truth value. So it was more going back and forth, let's say. But this is also kind of while using these tools, maybe you develop an intuition sometimes. But
Yeah.
just to mention here, it's not the same as generative AI that a lot of people have worked with that needs thousands and thousands of entries. Usually for this number of inputs and one output, that was enough in our case.
Okay. If there wasn't a need for creating the UI for Rhino, is it possible to do all the VS Code stuff inside the Rhino script editor directly?
Hmm. That's a good question that I don't know. Do you know, Pedro?
Mm, I think so. Why not? Maybe the next
That would
one
be
is,
interesting.
yeah, it would be nice to try it and to see what it if we find any
Hmm.
problems on it.
Hmm.
But I think that
Yeah.
it would be, theoretically, it would be possible, yes. You
It would be
do,
nice to move away from WPF and use another framework, but at Rio, for example, we're using React now for the UI in Rhino for Rhino plugins,
mhm.
which is makes some things easier.
Yeah, you can also use Ito in the script editor as well. So you can
Yeah.
create your own UI, native UI, without any other tools if you want.
Mm.
Okay, there are a lot of questions here. Okay. So if I understand correctly, that dependencies get directly installed in Rhino. Normally you have a virtual or conda environment to keep
Mm.
dependencies on a per project basis. Is this here also the case, or does it work differently?
No, it works a bit differently. So how Rhino people have set it up. You don't need to create an environment. It has a specified path with the installed libraries. So you just need to install the libraries once through these two ways I mentioned. So one is directly high level from the Rhino interface and installing the libraries from there. That is quite easy. And then if you need more advanced stuff, you can find the path. That was a screenshot I had with let me find it uh, with a PowerShell, the path that where Rhino saves all the libraries. And yeah, here. So this is the path. And you can access this from PowerShell and install the libraries there directly.
Yeah. And if you have problems importing any library, you can also contact us just to
Mm.
give you some help. So one from Leon, do you have any books or sources you can recommend about starting with ML in the context of the AC sector?
Mm. Yeah, no books in mind, to be honest, on the top of my mind. Um, Gabriela is teaching the seminar at Macad, which is exactly this process. Um, so I think you can join that seminar separately without like joining the whole masters, only that seminar from the masters. And it's also online and can be done asynchronous. So you can contact Macad from IAC about joining. But perhaps there are more resources that I'm not aware of, so I don't want to say that that's the only one.
Okay. Okay, any more questions? Okay, Ileana, let's close it up.
Mhm.
So thank you very much for preparing the presentation, for your time, and congratulations on your work, of course.
Thank you. Thank you very much, everyone, for participating, and thank you, Pedro, for inviting me.
Okay, great. Well, to the audience, see you in the next Rhino user webinar. So see you around.
Yeah, and
Thanks.
just to mention, if you
Yeah.
have any, feel free to contact if you think that process can be done in a better way. And also feel free to contribute to our GitHub repository because, yeah, we are not masters. We are always open to learn.
Great. Thank you, Elena.
Thank you. Bye.
Bye.